Good morning, good afternoon, good evening. This is Fazel Ganji from TU Kaiserslautern, Germany, from the Chair of Built Environment. Today I'm going to present the paper with the title Exploring the Potential of Dynamic Facade Systems. So, as an introduction, dynamic facade in general or dynamic sun protection systems have been around for a while, and they are promising solutions since they are able to respond to the environmental conditions and indoor parameters like occupants' behavior. So, selecting a shading system is a crucial design question. But for decision making, we need to do a better estimation. And we need to answer if it pays back the cost of installation, operation, and maintenance or not. But at the same time, we should not neglect the role of controllers because, as you know, manual control is not efficient. As you see also in this picture, people are good in pulling down the shades and turning the lights on, but they are too lazy to switch them off and pull them up again. So we need an automation. But there are many unsatisfying automated systems in the market, and the main reason is that they are not considering a multi-criteria for making decision. So for sure we need an automation system to balance daylighting, glare, heating, cooling, and lighting at the same time for individual view direction for individual people in a room. So in this project, the main objective was understanding the impact of dynamic shading on both energy and comfort. So first of all, we need to know the overall performance of glazing and shading systems in this project. We use a double glazing system with the U value about 1.3. And as we know, the advantage of a dynamic shading is that we can control the states of shading at every point of time, and this influences the performance metrics such as solar heat gain coefficient or G value and the transmittance in solar and visible spectrum. Keep in mind that the clear state of the window of the electrochromic glazing is much darker than the clear state of shading Venetian blinds when the shades or blinds are completely pulled up. And on the other hand, closed blind may have a lower solar heat gain coefficient, much lower than EC, and this may lead to a better solar protection in summertime. So considering three different zones, top, middle, and bottom, and possible states of shading for electrochromic glazing or Venetian blinds, we will end up to the total number of possible combinations for each system. 64 possible cases for electrochromic glazing and 13 possible cases for Venetian blinds. And we always need to answer the question of dynamic control, which is what is the best control input at every point of time for each window area. Here you see the 3D model which has been used in Radiance three-phase method and Transist dynamic simulation. We use an advanced integrated daylight and thermal simulation. Both benefits from advanced modeling techniques such as BSDF for complex fenestration systems such as Venetian blinds. As you see here, we have a very big window wall ratio, about 85%, which is very common for the office spaces. And we divided the window into three different zones, top, middle, bottom, which is helpful in terms of controlling and taking advantage of the shading system effectively. The only external surface is the south wall, which is the wall which we have the window on, with the U value of 0.19. 4 occupants has been considered with individual positions and view direction, which is used for MRT calculation and the glare and daylight simulation. And the set point for cooling and heating we used in this study is from 20 degrees centigrade to 27 centigrade, which is quite wide, and mainly because we wanted to focus more on the impact of shading systems in this study. So in simulation in general, the goal is normally to evaluate the effect of different inputs. And here we have our dynamic input, which is a time-dependent variable, and to see what is the performance of the building in different aspects of thermal comfort, visual comfort, and energy. So just as an example, for the middle part of the window, we need to specify control signals, not only for 1 hour, but for every hour over a year. What you see basically here is that control profile, which contains from 0 to 24 hours each day from January to end of December. Every point here in this carpet plot represents a state of the window for the middle part. And if we apply these control inputs into the simulation, we can see the performance of the building. Here, for example, we can see predicted mean vote, which represents the thermal comfort, and you can also see the impact of shading system on the outcome of the building. To evaluate the potential of shading systems, we need to generate different control profiles, different cases, different scenarios, and going through a what-if analysis to investigate the real possibilities of each shading systems. So in this case, we can generate these control profiles, and we can do multiple simulations and then do the multiple comparison to find out worst case scenarios and base case scenarios. And this will give us a better understanding of the behavior of the shading systems in our building. Generating different cases can be easy or can be sophisticated. As you see here in this study, we try to generate control strategies, static and dynamic, and we use not shaded as base case when there's no shading applied on the window, and no control, meaning that we leave the window always clear or always shaded, and also other dynamic strategies that we used in this study. At the end, we need to generate these control profiles to use them as an input to the simulation model. Some of these control strategies are easy to generate. As I said, the base cases are easy and no control, so we don't have any problem leaving the window always clear and shaded. And for manual operation and rule-based control, which is based on illuminance or radiation on the window, or based on the falling transmitted radiation on the workplace or on the subjects or on the occupants, we can easily check the hourly values of indoor temperature, outdoor temperature, radiation, illuminance, inside, outside, and generate this control profile over a year. However, generating our benchmark, here simulation-based control, which is a penalty-based ranking and selection algorithm, is a hard job, and I need to explain them briefly in the coming slides. So we use this control optimal control as our benchmark in this study. Okay, since we have this simulation framework, to find the most optimal control, we can pre-calculate all the building performances for all the possible shading combinations. Maybe it's not possible or practical for all for any general question, but in our case, as I said, it's still a very valid optimization method. So by generating all the results, we developed an algorithm which goes through and search through all the hourly results to find the most suitable solution at every time step. And it does the ranking and selection by using a penalty function and take out the optimal control profiles for each window area. This file can be recorded and captured as a CSV file, and this is one of the control profile we can use later in another simulation for generating the final results. Now let's take a look into the control optimization and how the penalty-based control works. The main goal is selecting the most appropriate window combination. One of the solutions for multi-objective problems in general is some weighted penalty function method that we also used here in this study. We have some priorities which we defined by weights, and we have some penalty function. You can easily extend this formula for any different aspects here. For example, visual comfort, thermal comfort, and energy saving is used. And for each cases, you can also define different performance indicators and individual weighting or priorities you can assign to each. So basically at every hour, we define this design space, which contains all the points or all the possible cases of the window, and it plots out the distribution of the points over these three aspects. What we can see is you can get the final output, which is a case with the minimum total penalty, and this represents what is the optimal window combination at this point of time. So if you repeat this process over every hour a year, you can finally generate this optimal control profile, which is the best performance of the shading system, and we can use it as our benchmark. Before going to the final result of this presentation, I want to mention that in the publication we have more number of cases, and you can find the rest of results there. And for the sake of simplicity, we only pick 3 main cases to show in this presentation. Let me summarize them. So first of all, we use some base cases. The window with no control and no shading, the blinds always up, and EC always in the clear state has been used as main base cases. Later we also pick radiation-based control as the classic control, which is commonly used in the market. And here we use the direct radiation on the facade, and the threshold is defined to switch the top and the middle window into middle tinted for EC and shaded 45 degree for blinds. We also kept the down part, the bottom part of the window always clear in order to provide enough daylighting inside the space. And on the other side, we use our benchmark, which was, as I explained, the penalty-based control or control opt, and it clearly shows the potential of an optimal automation control. And it can be a predictive controller, or it can be an advanced controller, which we will use in the building automation. Since comfort matters, let's start with the comfort results. First of all, we show the annual performance of shading systems in avoiding discomfort glare in here. And it's for a south orientation window. On the horizontal axis, we have different control strategies and different shading system, always blinds, EC, blinds, EC. And on the vertical axis, we see the percentage of dissatisfying occupied hours. It means that basically for the no control, we start by considering different view direction, and we calculate the DGP, or simplified daylight glare probability, and then we count the number of occupied hours with disturbing and intolerable cases. So the smaller the better. And as you see in the no control case, already the low TVs or visible transmittance in electrochromic glazing has already improved the glare protection. And for the other cases, the classic radiation-based control and our benchmark penalty-based control, we are able to avoid discomfort glare and keep it below 5% over the occupied hours. So next 5% is something is useful daylighting, and we need to know what is considered by the guide useful. When the amount of daylighting on horizontal workplaces is between 3000 lux and 300 lux, and there is no risk of discomfort glare or too dark space, we consider that as useful daylighting. The percentage of occupied hours, again, with too bright or too dark condition on the vertical axis has been calculated. So the smaller, again, the better. For the no control, with the lower visible transmittance of EC, you see a reduction of 8% in the too bright cases, basically the red one. But it made the room much darker, so we have an increase in the too dark cases as well. So in the radiation base and penalty base, we reduce the dissatisfying too bright number of hours, which is a successful job. If you compare the radiation-based control to penalty-based control, you notice that optimal control, or our benchmark, has more too dark number of hours. Of course, it's because the algorithm tried to reduce cooling demand at the same time. So useful daylight is not the only goal of this algorithm. By keeping these bars below 25%, we can achieve 3 points for LEED certificate, for example. So we have already achieved by applying those control strategy. To evaluate thermal comfort, we use predicted mean votes as an index, which is also called PMV. And as you know, this index is not only based on air temperature, but also considers mean radiant temperature, relative humidity, air velocity, and personal parameters such as closing metabolic rate. And when PMV goes beyond +1, it is considered as hot sensation, and when it is below -1, it is cold. And therefore, on the vertical axis, we have the percentage of dissatisfying occupied hours when the PMV is below -1 or above +1, which is the number of hours we want to keep them as low as possible. So for no control, with lower G value, EC improve thermal comfort feeling hot. For radiation-based control, feeling hot, or the red bars, for both blinds and EC is reduced, but at the same time, cold feeling is increased slightly. And in our benchmark penalty-based control, both avoided hours with hot feeling quite well. If you just notice the difference between blinds and EC and penalty-based control, you will notice that optimal control for blinds was more successful in avoiding hot feeling number of hours. And this is mainly because of the lower G value when the blinds are fully closed. If you remember, I noticed them in the earlier slides. So it is also suggested by the guidelines to keep the number of hours with dissatisfying thermal comfort below 10%, which is not completely succeeded here. And if you remember, we had a very wide range, and we only consider some constant personal parameters for this study. But it's a comparison study, and it's still valid, and it shows us the difference between cases. After talking about providing comfort, let's take a look into the impact of shading devices on saving cooling energy. The use of heat pump is growing significantly nowadays, and this is the reason we calculate annual end energy considering a chiller system in our study with the seasonal performance factor of 4. So the values you see on the vertical axis is cooling end energy with the unit of kilowatt hour per square meter over a year, so annual values. For no control case, with the lower G value, you see that EC clear state already saves more than 45% compared to the blinds up. It's a significant improvement. For the radiation-based control, the same way EC performs better than blinds, but as you see, for the penalty-based control, blinds performs slightly better than EC. And the reason is fully closed blinds are protecting much better than the fully tinted EC. If you remember, I have mentioned that based on the lower G value we receive by closed blinds compared to fully tinted EC. Now we have annual end energy for heating, considering a heat pump system. So for no control, this is basically the minimum heating demand we can have. There is no shading applied, and there is no tinting for electrochromic glazing. So this is the largest solar harvest we can have, solar gain we can have. And for radiation-based control and our benchmark penalty-based control, if you notice, the blinds performs better than EC, slightly. But why penalty-based control is worse than radiation-based control in this case? And the reason is the optimal control considers glare by activating the shading system during winter time, so during the heating period. This leads to a slightly higher heating demand. So the reason is that this algorithm tried to trade off between energy and glare protection. And last but not least, similar to the heating energy, we have electrical use for lighting energy. So no control, this is again the minimum lighting demand because we have achieved as much as possible daylighting in the room. And by applying the radiation-based control and the penalty-based control, you definitely have an increase. But if you notice penalty-based control, we consumes slightly more lighting than radiation-based control. And this is again due to its responsibility for glare protection. And always remember that the penalty-based control saves more cooling with relatively higher ratios. So it's okay if the lighting is slightly increased in this case. Finally, let's take a look into the overall end energy of the room with a south-facing facade. As you see, thanks to using an advanced control, here our benchmark, versus the standard control or classic control, which is a radiation-based control here in this study, it is possible to save this amount of energy, as you see in the with the green rectangles. Later, we can consider this amount of savings for investing on an advanced controller in buildings, for maintaining sensors, for developing a new algorithm. So this is the amount of money we need to estimate correctly for making final decision. Please go to the paper when you can see more results and more comparisons, such as even view obstructions and CO2 emissions for blinds versus electrochromic glazing. This presentation and publication was part of a project called LISA, funded by Federal Ministry for Economic Affairs and Energy in Germany. For the last 3 years, we have been conducting different experiments and studies in living lab at TU Kaiserslautern, and we developed a simulation-based framework for evaluating the behavior of different types of dynamic shadings. We use advanced tools such as Windows software, Radiance, and Transys, and some Python scripting for post-processing the result and linking these simulation tools. Taking a look into the overall results of this study, we can say that an automated system is able to exploit the full potential in both energy savings and providing comfort. And if we can achieve a well-automated electrochromic glazing or external Venetian blinds, they are both similarly satisfactory. Of course, in this case, in our study, blinds performs slightly better than EC due to providing a wider range of visible transmittance and solar heat gain coefficient, which means more daylighting and protecting against glare and heat gain when it is necessary. But in general, they may work well by having a good controller. So this means a cost estimation is really crucial for system selection decision making, and we need to be realistic by considering different scenarios for control and operation of the systems. But we did a study and we can conclude that the investment on advanced controllers can be paid back based on the scale of the project. Thank you for your time, and if you have any questions or comments, please reach us on the contact below, and have a good day.